Hello, my name is Jiří Šimonek and I'm from the company CFD Support, and I would like to show you how to set up and run a CFD simulation in the Turbomachinery CFD software. There is an outline of this presentation. At first, I will show you how to set up a CFD simulation. The next step will be running the simulation, including computational mesh generation. And the last point, which I'm going to show you, is an automatic evaluation of results. And what we need to start? The first thing we need is a CAD model of the machine we would like to simulate. Of course, it's possible to import an existing computational mesh, but I'll show you how to start from scratch with just a CAD model in an STL format, because Turbomachinery CFD reads models in STL. Open the ParaView, which is delivered within the Turbomachinery CFD package. Now we have to activate the Turbomachinery CFD source, TCFD source, which is a graphical user interface for Turbomachinery CFD. To do so, open Sources in the upper menu and find the TCFD source and click on it. And now the Turbomachinery CFD graphical user interface appears here on the left. At first, we have to click Apply to fully activate the TCFD graphical user interface. Let's move on General Properties. There is a file name entry with the case setup file. Because we would like to set the radial pump from scratch, we will not load any setup file, but we will create a new one. So click on Save As, and a Save dialog window appears. And now type here a name of a new file. For example, pump-test-1. And click OK. And the case setup file is saved with an extension .tcfd. And the last thing in the general properties is an appropriate machine type. So select the pump from the drop-down menu. Let's move on to components, which is the most important part of the case setup. Because here comes the CAD model and the topology of the case. You can divide your model into several components. In this case, there will be three of them: the inlet pipe, the impeller, and the volute part. So let's start setting the number of components to 3. You can see that we have 3 tabs now here: component 1, component 2, and component 3. For each component, we have to load the directory where we store their STLs. So let's do that for the component 1. We have to set a path to our STLs. So click on this button next to the STL directory file entry. The Open File dialog appears, and my STLs are located in the directory STL. I have here 3 more directories: impeller, which belongs to the impeller component, component 2, inlet pipe, the inlet pipe component, component 1, and volute, the third, the last component, with the geometry of the volute. So to load the STLs of the inlet pipe, I will click on the inlet pipe directory, in which I have 3 STLs: inlet pipe inlet, inlet pipe outlet, and inlet pipe wall. And to load it to the TCFD, just go one directory up, select the inlet pipe directory, and click OK. Now we can set the component name, for example, the inlet pipe. Number of periodic segments remains 1, because this is a full geometry and not just a periodic segment. And now let's go on and set the types of the boundary conditions. The inlet pipe inlet will be the general inlet. The inlet pipe outlet, double click on this field, will be the outlet interface, which will be later on connected with the inlet of the impeller. That is the next part, next component inlet, and inlet pipe wall will be the general wall. To connect the inlet pipe outlet with the next component inlet, just right mouse button click on this type field and select CO2, so it means the inlet pipe outlet, the outlet of the component 1, will be connected with the inlet of the component 2 that will be set in the future. Yeah, so that's it. And now if we click on apply, the geometry of the first component appears. So this is the inlet pipe inlet, inlet pipe wall, and here is the inlet pipe outlet. The next very important parameter is the background mesh size. It is a maximum size of the cell in the computational mesh. It is in the same dimensions as the geometry in STLs. So it means ours in millimeters. So let's set it as a 10 millimeters in each direction. So the direction in x-axis 10 millimeters, the direction in y-axis 10 millimeters, and the direction in z-axis, the 10 millimeters, the same. And the second very important parameter is an internal point, which determines where the computational mesh will be generated, whether inside or outside the geometry. Of course, it should be inside in the inlet pipe. And such point is, for example, 0, 0, and minus 115 millimeters. So let's click on apply, and we can move on to the second component. So select the component 2 tab, and let's do the same as for the component 1. So at first load the directory with the STLs that belongs to the component 2, which is the impeller. So select the impeller directory, click OK, set the component name, which will be, for example, the impeller. Number of periodic segments is 1. It's not a periodic segment, it's a full wheel configuration. And select the patches, the boundaries, by double-clicking on its type. So the impeller blades will be the blade type, impeller hub will be the hub type, impeller inlet will be the inlet interface, which will pair with the component 1 outlet, with the inlet pipe outlet, by right mouse button click and click on CO1. Impeller outlet will be the outlet interface, which we will pair with the component 3. So the outlet of the impeller will be the neighbor of the inlet to the volute, so which will be the component 3, and the impeller shroud will be the shroud. So that's it. Now click apply, and the impeller geometry will appear. And now we have to select which parts of the impeller geometry will rotate. So blades are the rotating part, so tick that this component is rotating, impeller hub is rotating, and the impeller shroud is rotating. Now a little bit more about the interfaces, the inlet interface and the outlet interface. Inlet interface of the impeller component is connected with the inlet pipe, and here the last number, the last column with the number zeros here defines either the interpolation between those two components or we can use the mixing plane boundary condition here. So if there is a 0, it means there is an interface which interpolates from both sides, and if the number is higher than 0, then the mixing plane interface will be used with the number of mixing plane stripes or mixing plane segments defined by this number. So for the impeller inlet we will not use the mixing plane, we will use just the smooth pairing, but for the impeller outlet we can use the mixing plane approach. So double click on it and set, for example, 5 mixing plane stripes. Now we have to set the whole component as a rotating component, because the whole impeller will rotate. The next thing is the background mesh size. We can set the same background mesh size as for the first component, so 10 millimeters in each direction. And the most important thing is the internal point, which will be, for example, 50, 80, and 60. Here we can see in this figure that could be enlarged by double clicking on it, the scheme of the component setup, and this means that there is an inlet pipe, the outlet interface, inlet pipe outlet that is connected with the inlet interface of the impeller inlet. Impeller is a rotating part, and there is the impeller outlet that will be connected with the component 3 that we are now going to set up. Go up, select the component 3 tab, load the STL directory with the STLs of the component 3 of the volute. Set the component name, for example, to volute. Click apply. Set the type of the volute inlet. That will be the inlet interface, which will connect with the component 2. Volute outlet will be general outlet. There is no one component connected to the volute. Volute RSI connection is a wall, and volute wall is also wall. None of those are rotating boundaries. It's not a rotating component. So when we click apply, the geometry of the volute appears. So now we can see the whole geometry of the pump. The next thing that we have to do is to set the background mesh size. Let's set it as a 10 millimeters as in component 1 and component 2. And the last thing that is missing is to set the internal point, which is 50, 200, and 60, for example, for the volute. So, and that's it. We can check the component map. All the arrows are full, so it means everything is set properly, and we can move on now for the next setup. So close the components setup window and open the coordinates. There is an origin and axis. We can leave here the default settings because it's an origin of the rotation axis that goes through the origin of the coordinate system, and the axis of rotation is z-axis. So this is okay, and we can go on to the geometry setup. There is a scale factor, and we have to change the scale factor from 1 to 0.001 because we would like to scale the geometry from millimeters to meters, because we have to always compute with meters. So once the geometry is generated in millimeters, we have to scale it with a scale factor that is 0.001. We can leave the default for the rest, and we can move on the physics. There are mainly the fluid properties. We can leave the defaults here because everything seems fine for our pump simulation. Water as a fluid, atmospheric pressure as a reference pressure, and 293 Kelvin as a reference temperature seems fine as well. So let's go for the turbulence setup. Here you can choose the turbulence model. There are three options: laminar, K omega SST, and K epsilon. I like K omega SST, works really well in the most of the turbomachinery cases. So let's choose K omega SST. And now we want to continue with a speedline setup. Here we can choose how many different speedlines, it means rounds per minute, you would like to simulate, and how many points, for example, different flow rates for each speedline you would like to simulate. I will set just one rotation speed, so it means just one speedline, and I will set it, for example, for 1800 rounds per minute. Let's set 5 speedline points. We will set 5 different flow rates for each of them. And let's keep 500 iterations for each point for this test case. And now it's time to move to inlet boundary condition setup. Set inlet boundary condition as volumetric flow rate. And we will set 5 volumetric flow rates. So the first 0.18 cubic meters per second, 0.17 cubic meters per second, 0.16, 0.15, and 0.14. Turbulent quantities are fine as they are by default. So we are done, and here we can move on the boundary conditions at the outlet. Leave here the fixed pressure boundary condition, and also leave 0 pressure for each point here. Because our simulation is set as incompressible, so we can count just with pressure difference and not the exact pressure values. It is usual to use 0 pressure at the outlet when the simulation is incompressible. So let's continue with the simulation setup. Our simulation will be steady state. I can use just the 2 processors because I have 2 here. Minimum pressure, maximum velocity are bounding values for the calculation. These are values that can't be exceeded during the simulation, otherwise there will be bounded to those values, and the defaults are fine for this pump simulation. Numerical order. Here we can choose whether we would like to use first order discretization or the second order. Let's keep the first order for simplicity at the moment. Convergence check can automatically stop the simulation when the convergence criteria are met during the simulation. Numerics, there are just relaxation factors and the defaults are fine. Initial conditions, except the initial pressure that we shall change to 0, like the pressure on outlet, we can keep the defaults. So just change the initial pressure to 0. And Now we can leave the rest of the setup as default for now, and we can start the simulation. So let's go up and let's save the setup by clicking on Overwrite, and let's continue with the running of the CFD simulation. To run the simulation, we have to activate the TCFD manager that will be loaded after pressing this icon. Now click Apply to activate the TCFD manager, and there's the window with the geometry, and here is the window where will be the simulation report after the simulation will finish. We have to provide the directory name here, for example pump test 1. Click Apply and click Write Case, and the case is written now on your hard drive. And for automatic run, just press Run All. It will start the meshing, then it will run the CFD simulation, and when the simulation is finished, it will automatically evaluate the results, and it will generate the final HTML report. So let's click on Run All and wait what happens. Now we are in the middle of the meshing phase. The mesh of component 1 and the mesh of the component 2 are already generated. And once the last component will be meshed, all the meshes will be merged together and the meshing phase will finish. The mesh has been generated successfully and the CFD simulation is running now. There are progress bars with the estimated time after which the simulation will be computed. The first row is related to the 1 point, in this case to 1 flow rate, the speed line for the all flow rates at the given RPMs, and the total time to finish. We have 1 speed line, so that's the reason why the speed line progress bar and the overall progress bar are completely the same. The simulation finished successfully, and the simulation results were automatically evaluated and put to the final report. We can check the final report here on the right. So, and that's all from this video. I believe it was useful for you to watch it, and feel free to contact us if you have any specific questions. Thank you for watching.